And I'm on chapter 3. That's because I did 2 chapters last time for some reason. I'm not exactly sure why. I probably should have stuck with the schedule. But since we're ahead, let's go ahead and stay ahead. So let's go ahead and tackle chapter 3. Don't feel like you need to keep up with me. You can keep up with the schedule. Everything is going to work out in the end. Somewhere down the line where I would tackle 2 chapters, I will only tackle 1 and we'll get back on schedule. But it's going to be in the middle of the semester. So don't worry that I am lecturing ahead of schedule. That's fine. Um, this is a kind of a complex chapter. So putting this one together with chapter, oh, I guess we weren't supposed to do that. I kind of got my wires crossed. I was teaching this class in the summertime, and for some reason, they gave me that schedule, the 10-week schedule instead of the 15-week schedule. Let's not worry about it. Let's go ahead. Chapter 3, we'll tackle that right now. This is a really interesting and important chapter. It's important to understand neurophysiology because this is how medications work. This is why medications work. We will give you some kind of a substance. It will have cations and anions. Cations are positively charged substances or molecules, and anions are negatively charged molecules. And that substance will change some structure in your body that will change the way things work. For example, I take blood pressure medicines. As a matter of fact, I just took it. And my blood pressure medicine lowers my blood pressure. How does it do that? One of the ways that it does that is by changing the the action potential of the blood vessels or the cells in my heart. So the neurons, instead of firing all the time because of the stress that I'm under, they don't. They just don't fire. It takes a lot more stress to get me excited than it would have if I weren't taking the medication. And it's all a chemical it's all a chemical reaction, and that probably keeps me from having high blood pressure. So there you go. Another example would be if you're depressed, we can give you a chemical, selective serotonin reuptake inhibitor. It will inhibit the reuptake of serotonin, which allows there to be more serotonin in the synaptic cleft. The more serotonin equates to you as not feeling nearly as depressed. It puts all this positive chemical in your system, and since it's more positive, since this chemical makes you feel more positive, then your depression goes away. This is the way pharmaceuticals tend to work. Um, Sometimes we rely a little bit too much on pharmaceuticals. Sometimes we should probably be trying to change our way of doing things through exercise and positive thinking. But well, let's not worry about that. Let's not worry about the direction medicine has taken over the last 200 years. Let's go ahead and get into the chapter. Electrical signals are the vocabulary of the nervous system. Molecules that maintain an electrical charge are called ions. Positively charged molecules are positively charged are cations, and negatively charged are anions. Um, an example of a positively charged cation, a cation, would be sodium and potassium. Those are both metals, and because they're metals, they're positively charged. An example of a anion would be chloride. So when we create substances, what we have to do is stick a positively charged molecule is attracted to a negatively charged molecule. Um, when they bind together, then they create a substance. And in this case, if we put sodium and chloride together, we get salts. And if we put potassium and chloride together, we get salt. It's also salt. But most of the salt in the world is sodium chloride. Anyway, okay. Once upon a time, they tried to put chloride together with lithium, and they created lithium salts. They were thinking that since we have had so much depression, if we created lithium salts, it would make everybody, it would normalize everybody. It would make people less depressed. And one of the things we did was poison people. Sodium's okay. We can handle sodium, but lithium is another type of heavy metal, and it poison people. So that was not a good idea. It was an experiment that went awry, as it were. So let's go ahead and take a look at fight or flight response, and they will explain all of these things about electricity, and well, they're not actually going to do that. Okay.
Signals from our environment are most often first detected by the brain. When someone is frightened, a stress response is initiated by their reaction to an environmental signal. But many signals don't stop here. A signal received by the brain can be passed on to many types of cells throughout the body and have widespread effects. Signals get sent around the body by traveling through the nervous system or bloodstream, going from cell to cell. You could think of the cell's sole purpose in life as keeping signals going or initiating new ones in response to the environment. Once a signaling molecule from the bloodstream reaches a cell and docks, the signal is passed into the cell. Like a miniature mousetrap game, the cell is filled with complex contraptions called proteins that bump and nudge each other to keep the signal going until it reaches its target. In this case, it's the production of yet another signaling molecule that will get released into the bloodstream, dock on other cell types, and cause them to react in a variety of ways. The signal-passing machinery inside the cell can look and work very differently, depending on the intended effect. Here we see a signaling cascade that results in the release of energy molecules. Once liberated, they are sent on their way via the bloodstream to power cells in another area of the body. When this tiny domino effect is triggered inside cells, some amazing things can happen. Other signaling cascades triggered during the stress response result in a variety of physical reactions. This signaling molecule can relax or contract different types of muscle cells. When it reaches the skin, the signal docks on muscle cells attached to a body hair. The tiny muscle is stimulated to contract, raising the hair. The signal also docks on cells wrapped around a sweat gland, which contract too, squeezing sweat onto the skin's surface. In the lungs, the signaling molecule docks on muscle cells wrapped around bronchioles. But these cells relax instead of contract to allow more oxygen into the blood. Because the protein machinery inside each kind of muscle cell is different, this single type of signaling molecule can cause both relaxation and contraction. Many signaling molecules work this way. When this signal reaches the heart, it docks on beating heart cells. Their response is to beat faster. Blood pressure goes up, and the signaling molecule is rushed on to still more cell types around the body. Constantly and in concert, cells must send and receive a myriad of signals. Cell communication is vital to keeping the body alive.
Okay, so now you understand why I take blood pressure medicine. It's to slow down my heart rate. And my heart rate's relatively slow. I can look at it right now. 54. 54 is not too bad. And that potentially keeps me alive or allows me to live longer than I would have otherwise. Neurons contain large complex proteins that maintain a negative charge. But because the channels are closed to the larger positively charged sodium molecule, only the smaller positively charged potassium ion can pass through the small channels. Potassium is a much smaller molecule, therefore it can get through, but the sodium cannot. The human body, if you taste somebody on the inside, it tastes like salt. That's because the natural fluid in your body is what they call normal saline, or it's has salt in it. Tastes like salt. Because of the larger negatively charged proteins, a neuron at rest maintains a negative resting potential of from 50 to 80 millivolts, with the average of negative 70 millivolts. Now we're going to watch a film in just a second. It's going to say 40 to 90. Really all depends on the neuron as to what the resting potential is. 50 to 80, 40 to 90, that's, it's kind of a shooting match out there. But the average tends to be right around negative 70. Negative 70 millivolts is the potassium equilibrium potential as equated by the Nernst equation. There are many more potassium cations inside the cell than outside, while there are far more sodium cations outside than inside. So the one thing that you need to remember as we're watching the next film is that sodium, there's a lot of sodium in the world. The oceans are full of salt water. Each individual, whether it's an animal or whether it's a human, whether it's a lower form of animal, everything tastes like salt. So there's a lot more sodium out there than there is anything else. So inside our bodies, it's salty, and that's how we maintain ourselves. If we don't take in enough salt, if we lose too much salt, sodium chloride, then our neurons can't function properly, and you see that from time to time. People exercise a great deal, like running a marathon or something. Sometimes they will have a problem. Some people, when they start to run a long distance, they decide, well, I need to hydrate, so I'm going to drink a lot of water. Well, that can cause a problem as well, because instead of having too much salt, now we don't have enough salt, and it actually can cause the individual to collapse and die, because you need those neurons to fire in order to function properly. So drinking too much water, it's called, what is it called? Hypernatremia is what it's called. Can cause just as much damage as not having enough salt. And that's one of the reasons. When I was in the military, they used to give us salt tablets because we sweat so much. They didn't want us to collapse, and it would have happened. It would have caused a lot of trouble if we didn't have enough salt in our systems. So another interesting thing about military food is that it has a lot of salt in it. And of course, you get used to that. You get used to a lot of salt. So it's really kind of interesting. When the neuron is stimulated by a neurotransmitter detected by a dendrite, the chemical neurotransmitter causes localized depolarization. In other words, the neurotransmitter causes the sodium channels to open in the immediate area. And remember, there's lots of sodium on the outside. So in order for a for a neuron to fire, they have to open up the sodium channels, and now it becomes a lot more positive. So the resting potential is -70, and all of a sudden we have this flood of sodium coming in, and since the sodium molecules are positively charged, the flooding in of the sodium molecules makes the neuron positive. So the resting potential is -70. Now we're going to flood in enough sodium to create a action potential of +40. So that much sodium is coming in. It creates a change of 110 millivolts. It goes from -70 to +40, which means that's 110. If you add the two of them together, that's 110. For a neuron to react, it must receive an adequate amount of neurotransmitter to stimulate enough sodium channels to open up. This is referred to as the neuron's threshold, usually a depolarization of -50 millivolts. If the threshold is reached, then enough sodium channels will open to trigger depolarization. A neuron cannot partially fire, or it either fires or it doesn't. This is known as the all or nothing property. When the threshold is met, sodium ions flood into that portion of the cell through the rapidly opening sodium channels. This triggers the sodium channels next to the stimulated area to depolarize as well, causing a chain reaction along the neuron until it reaches the neuron's own synaptic cleft. So we have a chain reaction taking place. One sodium channel opens up. We get a flood of sodium ions coming in, cations coming in, and that causes the next one to open up as well. And we get this chain reaction all the way down the neuron. So we're going to see this. This is a short film. If I had, okay, let's do this again. There we go. Okay. We won't have to watch the advertisement. Maybe. Not sure what the crickets are all about.
Unstimulated, neurons maintain a constant electrical difference or potential across their cell membranes. This potential, called resting potential, is always negative inside the cell and ranges from -40 to -90 millivolts. If a neuron is stimulated, the negative potential inside the neuron can be made either more or less negative depending on the stimulus. If potential is made sufficiently less negative, it reaches a level called threshold, and an action potential is triggered. During the action potential, the neuron suddenly becomes 20 to 50 millivolts positive inside. Action potentials last a few milliseconds before the cell restores its negative resting potential. The cell membrane of a neuron encloses cytoplasm with various ions dissolved in it. The neuron itself is immersed in a salt solution, the extracellular fluid. The ions of the cytoplasm consist mainly of positively charged potassium ions and large negatively charged organic molecules, such as proteins. Outside the cell, the extracellular fluid contains mostly positively charged sodium ions and negatively charged chloride ions. Since charged particles cannot pass through the lipids that make up cell membranes, they must travel through channel proteins that extend through the membrane. In an unstimulated neuron, only potassium ions can cross the membrane, traveling through specific proteins called potassium channels. Although sodium channels are also present, in unstimulated neurons, they remain closed. Since only potassium ions can cross the membrane, and potassium ions are more concentrated inside the cell, they diffuse out of the cell, leaving the large negatively charged organic ions behind. As more and more positively charged potassium ions leave, the inside of the cell becomes increasingly negative. But since opposite charges attract, as potassium ions diffuse out, an electrical force develops that tends to pull them back inside. At some point, the diffusion of potassium ions out of the neuron due to concentration differences is balanced by the electrical attraction tending to pull them back inside. This is the point at which neurons reach resting potential. Reaching resting potential in this way does not require significant changes in the potassium concentration inside or outside the cell. Only about 1/10,000th of the potassium ions initially inside a neuron must leave to create a resting potential of -60 millivolts. But it is action potentials, not resting potentials, that carry information through a nervous system.
Okay, one of the things that it looked like everything was going really slowly, but all this stuff takes place. All this equilibrium, all this balance takes place in milliseconds. So if a neuron fires, it goes back to its resting potential very, very quickly. So quickly, well, it's milliseconds. Excuse me. Action potential refers to the amount of positive ions that are allowed to flood into the stimulated area of the cell through the sodium channels before the sodium channels close. The action potential for most neurons is somewhere in the range of positive 40 millivolts. This is what I was saying before. So it starts out at -70, goes to positive 40, so that's how much of a change there is, 110 millivolts. When enough sodium ions flood in to reach the positive 40 millivolts, the sodium channels will close. Going beyond equilibrium with the outside environment is called the overshoot phase, and of course it looks like this is taking a lot of time, but like I said before, it goes from negative 70 millivolts to positive 40 very, very quickly, and then it returns back to its resting potential extremely fast. While a neuron is recovering from stimulation, it cannot be stimulated. This is known as the refractory phase. During the refractory phase, the sodium channels have closed, shutting off the supply of sodium ions flooding into the neuron, and potassium channels will open. Because the electrical charge outside the cell is more negative than inside the cell, potassium ions are drawn out of the cell. That's what we just heard in the video. With the positive potassium ions now flooding out of the cell quickly loses its positive charge, and it not only reaches its resting phase potential, but it goes beyond it in a phase known as the undershoot phase. But the potassium leak channels now allow enough potassium ions to re-enter the cell to return the area into its resting potential. But like I said, this happens very, very rapidly. Neuron dendrites and somas usually have a different type of membrane than axons. Dendrites and somas usually have sodium channels that are stimulated by chemicals and not by voltage. In other words, they are only activated when the chemical neurotransmitter is present. The axon, on the other hand, does have voltage-gated sodium channels, so the axon responds to stimulation from the dendrite and the soma. Neurons in the central nervous system are myelinated by oligodendrocytes, and neurons on the peripheral nervous system are myelinated by Schwann cells. The myelin covering of the neuron does not allow the potassium leakage from the area covered by the myelin. The depolarization voltage is channeled down the axon from one node of Ranvier to the next, increasing the response by as much as 15 times. This form of conduction is known as saltatory conduction. Multiple sclerosis is an autoimmune disease where, due to a genetic flaw or environmental trigger, an individual's immune system destroys the myelin on select neurons. This causes the slowing of motor movements and the loss of sensory abilities due to the slowing of the neuronal response because of the damaged myelin. Most synapses are triggered by a chemical neurotransmitter in the synaptic cleft, but researchers have discovered that some synapses in the brain are stimulated by electrical responses from another neuron. This is able to occur because the synaptic cleft of these neurons is 1/10 the distance of a chemical synapse. Not all neurons cause their connecting neuron to fire. Some neurons are inhibitory neurons, and instead of raising the excitatory potential, depolarizing the neuron, it lowers the excitatory potential, it hyperpolarizes the neuron, making it more difficult for the neuron to fire. So an inhibitory neuron would make the inside of the neuron more negative. And since it is more negative, it's going to take it more of a stimulation to fire the neuron. I hope that makes sense. So we're looking at a resting potential of -70. If there's an inhibitory neuron that's around it and it fires, then what it will do is it will increase the negativity of that neuron, making it, instead of -70, making it 110, -110 or 120. So you see what I'm talking about. It hyperpolarizes it. It forces it to have more stimulation in order for it to fire. Inhibition is done by inducing channels in the receiving neuron to open, allowing more negative chloride ions into the neuron. Since the chloride ions have a negative charge, they lower the neuron's potential to fire. An inhibitory or excitatory neuron is determined by the neurotransmitter they produce. Some neurons have hundreds of other neurons feeding into them. With these neurons, they may require a number of neuronal stimulations before their threshold is reached. This accumulation effect that is required for stimulation is known as spatial stimulation. Spatial summation. Summation just means addition. So this has to do with spatial. Some neurons that require an increased threshold will not react from a single neuron stimulation. However, if the single neuron fires in rapid succession, the accumulative effect of the neuronal stimulation will stimulate the neuron to fire. Because it is a matter of adequate stimulation in a select time period, this type of stimulation is called temporal stimulation or temporal summation. Time. Since a threshold has to be achieved before a neuron will be stimulated, there are various structural factors that can increase the likelihood that a neuron will be stimulated. The number of dendrites receiving stimulation increases the probability that the threshold will be reached. If a glial cell overlaps the synaptic terminal, it may increase the amount of neurotransmitter in the cleft by not allowing leakage. A chemical synapse works in the following manner. The electrical charge travels down the axon to the axon terminal. The charge changes the permeability of the calcium channels, allowing calcium to enter the synaptic terminal. The calcium causes the synaptic vesicles to fuse with the terminal membrane, releasing the chemical neurotransmitter contained in the vesicles into the synaptic cleft. So now we've got four chemicals that we're dealing with. We're dealing with sodium, of course, in the sodium chloride that's surrounding the neuron. We have potassium on the inside that is creating it is the chemical that creates the equilibrium on the inside of the neuron. And now we have calcium, and calcium is what is discharged in order to fire the neuron, calcium. And as you can see, it has two positive molecules. So calcium comes not in a single molecule, but it comes as a dual molecule. Ca2, or Ca++, that's the way we used to write it. After the release of neurotransmitter into the synaptic cleft, the chemical migrates to the receiving neuron and attaches to transmitter receptors that either inhibit the potential of the receiving neuron or stimulates the neuron to reach its threshold and fire. Much more neurotransmitter is released in the synaptic cleft than can or will be used. So it just opens the vesicles and it just floods out. How much is going to be used? Well, there's only a certain number of receptor sites on whatever it is that it's stimulating. Another neuron, a muscle, whatever it's trying to stimulate. There's only so many receptor sites. So despite the fact that so much chemical is released, it can only attach itself to a select number of receptor sites. Getting rid of excess neurotransmitter in the synaptic cleft. Since neurotransmitters left in the cleft will cause spasming of the neuron, it must be removed from the cleft. The amount of neurotransmitter is detected by the autoreceptor and triggers a stop of the release of the neurotransmitter. So now we've stopped releasing that chemical, but there's still chemical in the synaptic cleft. So what we need to do is we need to get rid of that chemical. And there's two ways that we do that. Removing excess neurotransmitter from the synaptic cleft is done in one of two ways. Either an enzyme in the cleft breaks down the excess neurotransmitter, or receptor sites in the transmitting neuron bind with the neurotransmitter and reuptake the neurotransmitter. Neurotransmitter that is taken back into the neuron through reuptake is recycled by the neuron. And this is the way that we are treating depression. We have a selective serotonin reuptake inhibitor. In other words, it inhibits the reuptake of serotonin, allowing there to be more serotonin in the synaptic cleft. So we have a substance that inhibits the reuptake of the serotonin, and that's what SSRIs are. Prozac, Zoloft, Paxil. These are all selective serotonin reuptake inhibitors. And selectively, they don't allow the serotonin to be taken back in to the neuron, leaving more serotonin in the synaptic cleft. The neurotransmitter binds to a receptor molecule on the receiving neuron. Each neurotransmitter, or ligand, has different receptor molecules that they bind to, called a ligand binding site. In other words, this is a chemical that can only be bound. I'm sorry, I don't have an arrow. Let me do this again. Give me an arrow. Okay. This is the ligand, and the ligand can only bind to this receptor site. There are other receptor sites on that neuron, but this chemical can only bind to this receptor site. And that's in German, and that's why things are spelled a little funny. When an excitatory ligand is bound to the receptor molecule, it opens up a sodium channel in the receptor molecule, allowing sodium to enter the neuron. So now we're firing the neuron. How does it do that? The chemical attaches itself to the receptor molecule. The receptor molecule opens up the sodium channels, and now we have a reaction. If enough receptor molecules are stimulated by an excitatory ligand, the neuron's threshold will be reached and the neuron will respond with an electrical charge. If the neurotransmitter is an inhibitory ligand, it will open up a chloride channel in the receptor molecule and chloride will enter the neuron, making it more negatively charged. Neurotransmitters are chemicals. While each receptor molecule binds exclusively to their neurotransmitter, there are similar chemicals that are structurally similar to the neurotransmitter that can bind to the receptor molecule as well. Acetylcholine is an excitatory neurotransmitter with the poisons curare from the South American plant, and bungarotoxin from the Bungara snake of Taiwan bind to the receptor molecule, causing paralysis. So what normally allows you to move, what normally allows you to run through the jungle or through wherever you are, if you are stricken with this curare, they put it on arrows, it will paralyze you. And then, of course, if it paralyzes you enough, then your heart stops beating, and now you're dead, and now they can eat you. Same way with the snake. If it bites you, then it puts a bungarotoxin into your system. It stops the acetylcholine from functioning. It binds to the acetylcholine receptor sites, and that, of course, will cause paralysis. And as far as the snake is concerned, it hopes that it stops your heart from beating. Acetylcholine receptor molecules are also the targets in the case of the poison muscarine from the Amanita muscaria mushroom, and this is what it looks like. It's got a red top. Muscarine, however, binds to the receptor molecule and mimics acetylcholine, causing the neuron to fire, resulting in spasms to seizures to death. Chemicals that mimic neurotransmitters and cause a similar reaction are known as agonists. Chemicals that mimic neurotransmitters and block the action of the neurotransmitter are called antagonists. And here is a video that deals with that. It's kind of a goofy one. Good job.
Our presentation is on agonists, antagonists, and receptors. A receptor is a chemical structure on the outside of a cell where an agonist or antagonist binds in order to send the cell a message. An agonist is a molecule that can activate a receptor to send the cell a message. An agonist is non-competitive, binds irreversibly, or competitive, binds reversibly.
Hi, we're talking about receptors. A receptor is like a keyhole in a door, and an agonist will bind like a key and it go into the door, and you will be able to go inside, like a message.
Antagonist, a molecule that binds to the receptor to block the agonist or antagonist and stop the message from being sent to the cell.
Hi, an antagonist is like the wrong key that will go into the keyhole, but it will not turn. Therefore, the message cannot be sent. I guess we're at the wrong house.
Okay, this information is important for nurses to know because you may be giving drugs that can act as an agonist, which will promote a physiological response to continue, or you might be giving an antagonist, which will make a physiological response stop. An example is when a person has an allergic reaction, they're producing histamine, which is the agonist, and you want to give them an antihistamine, which is the antagonist and stops the allergic reaction.
Ha-choo!
Here's some Claritin, which will stop that allergic reaction from happening.
Thank you, nurse.
You're welcome. Now hold it.
That was obviously a video by the nurses. University of Texas at Ashland, wherever that is. Okay, that was great. Okay, good job. Now we understand receptors, antagonists, and agonists. Thank you, nurse. Oops. Acetylcholine molecule receptors are referred to as cholinergic. Acetylcholine has at least 4 functions and binds to at least 4 cholinergic receptors. Acetylcholine acts on the neurotransmitter, the neuromuscular system as an excitatory neurotransmitter, and it allows you to move. Acetylcholine acts on the vagus nerve and the heart muscle as an inhibitory neurotransmitter. It slows down the heart through the vagus nerve. Acetylcholine is used by the brain in the transfer of memory from short-term to long-term memory. So it allows you to remember things. Acetylcholine acts as an inhibitory neurotransmitter to induce sleep. Acetylcholine shares some of its receptor sites with other chemicals, and for this reason, the receptor sites are named after the alternate chemicals. For example, nicotine binds to the acetylcholine sites in the skeletal muscle and the autonomic ganglia, and for that reason, these sites are referred to as nicotinic cholinergic receptors. Muscarine cholinergic receptors also exist in the autonomic nervous system. Muscarine kills by stopping the heart and paralyzing the intestines. There are two types of molecule receptors: ionotropic, ion moving, that's what ionotropic means. Receptors open ion channels and allow them to pass through. Metabotropic means change, moving. Receptors activate molecules known as G proteins. G proteins bind to the amino acid guanine in its many combinations. These guanine compounds may themselves open the ion channel or be part of a chain of reactions that open the ion channel in turn. So we have ionotropic, which tend to be relatively rapid, and metabotropic, which tends to be relatively slow. When we were looking at, when we were watching the video dealing with stress, the fight or flight response, and we saw all those reactions taking place, that was a metabotropic reaction. It tends to be relatively slow. Ionotropic is very rapid. There are four types of neuronal circuits: neural chains, positive feedback circuits, negative feedback circuits, and oscillator circuits. The simplest neuronal circuit is the neural chain. A sensory neuron is activated by a stimulus, and it in turn activates a motor neuron that responds to the stimulus. It's a very simple chain. One thing happens, the other thing happens. Boom, boom. Neural chain. In a positive feedback circuit, the effect is to increase an activity or keep it going. In a negative feedback circuit, the effect is to stop an activity. In an oscillator circuit, the circuit serves as both a positive feedback circuit and a negative feedback circuit, depending on the circumstance. Most sensory neurons collect data, converge the input through a single neuron, and then diverge the signal when it arrives in the brain. The eye does this. Each moment of sight involves over 100 million receptor neurons that converge the information into the optic nerve. It transmits it to the brain so that the signal can be diverged into various parts of the occipital lobe for interpretation. And that's what you're seeing right now. You're seeing 100 million receptors activating, and that's what you're seeing. You're probably not only seeing your screen, but you're also seeing whatever, you have peripheral vision at the same time. So you're pulling in information all over your retina, and your retina is sending this signal back to the occipital lobe. It's taking all these tiny little pixels of information, and it's creating a picture, and that picture is what you see right now. The electroencephalogram, the EEG, is a device that reads the electrical impulses put off by the neuronal activity in the brain. EEGs are used to map brain functioning and can be used for sleep analysis or to monitor abnormal seizure activity. In case of a coma, the EEG will detect lack of activity. 30 million people worldwide suffer from epilepsy. Epilepsy is characterized by seizures. Seizures are involuntary synchronized excitation of large groups of nerve cells in the brain. Seizures can be triggered by trauma or injury to the brain, chemical changes derived from metabolic faults, exposure to toxins, mutations in ion channels. Epilepsy is characterized by various types of seizures. Grand mal seizures are the most extreme form of epilepsy. Grand mal seizures are characterized by total muscle contraction followed by alternate jerking and relaxation. The seizures normally only last 1 to 2 minutes, but recovery may take as long as several hours. Petit mal seizures are characterized by losses of awareness of from 5 to 15 seconds, and it rarely means, it's rarely noticeable, the petit mal. It's just like a blackout for 5 or 15 seconds. Petite means small in French. Grand means, of course, large. Okay. Complex partial seizures do not involve the entire brain. The individual may experience an aura, a perceived sensation that precedes the seizure. Certain personality traits often accompany complex partial seizures, but it is not certain whether the traits trigger the seizures or the seizures trigger the traits. When I'm talking about an aura, a lot of times it has to do with odors. They'll suddenly start smelling an odor. The odors usually are negative. They're fairly foul as far as the individual interprets them, like rotten eggs or manure. Usually has to do with something rotting. So when they smell that, they know that they're about to have a seizure, and a lot of times this is a warning to them. Sometimes the aura will be visual, so they'll not only have this smell, but they'll also have a taste in their mouth, and they will see a a light. It's usually uh, a light behind something, as weird as that may sound. And this is an individual who is having a seizure. As you can see, I don't have an arrow. There we go. As you can see, this is the area of the seizure right here, and this is a normal brain. And there you go. It's just an electrical charge. Tends not to last for very long, maybe 1 or 2 minutes. I grew up with an individual who had epilepsy, so even even when we were in the first and second grade, we were taught how to deal with George when George was having a seizure. Um, in the old days, they used to tell you to secure their tongue because you can't stick your finger in somebody's mouth because they'll bite down. But he would carry tongue depressors in his pockets so that you could stick the tongue depressor in there and secure his tongue. Now they don't do that anymore. There's always a possibility he'll bite down so hard he'll damage his teeth. Anyway, I grew up with somebody with seizures, and that is the end of the chapter. So we'll go ahead, and I'm sorry that I'm ahead. Next week we'll tackle chapter 4, even though I think it says that I should be on chapter 3.